Look up at the night sky on a clear evening, and you might see a faint smudge of light near the constellation Andromeda. That smudge is a galaxy containing 1 trillion stars, each one a sun, many with their own worlds, and it's the farthest thing you can see with your naked eye. 2.5 million light-years away, it's our nearest large galactic neighbor. And despite everything we will ever build, every technology we will ever invent, every law of physics we will ever discover, we will never go there. Not in 1,000 years, not in 1,000,000, not ever. This isn't pessimism or defeatism. It's physics. The universe itself has locked the doors, and there is no key. We are trapped not by our limitations, but by the fundamental architecture of space-time, energy, and cosmic expansion. Most of the universe isn't just unreachable because it's far away. It's unreachable because the space between us and it is expanding faster than light itself can cross it. We live in a cosmic prison with walls made of relativity and cosmic expansion, and the sentence is permanent. If you love deep dives, you can subscribe. It helps more than you think. To understand why intergalactic travel is impossible, you first need to grasp just how incomprehensibly vast these distances really are. Our own Milky Way galaxy is about 100,000 light-years across. That means light, traveling at 300 million meters per second, the fastest speed possible in this universe, takes 100,000 years to cross from one edge to the other. Think about that for a moment. Light can circle the Earth 7.5 times in a single second. It can reach the moon in just over 1 second. It reaches the sun in 8 minutes. And yet, it takes 100,000 years to cross our galaxy. If you could somehow travel at the speed of light, which you can't, and we'll get to why in a moment, it would take you 100 millennia just to traverse our home galaxy. But let's put that in perspective using something we've actually built. The fastest spacecraft ever constructed by human hands is the Parker Solar Probe, which at its peak velocity reaches about 190 kilometers per second relative to the Sun. That sounds incredibly fast. It is fast. It's over 400,000 miles per hour. At that speed, you could travel from New York to Tokyo in less than a minute, but it's only about 0.064% the speed of light. At that speed, crossing the Milky Way would take roughly 150 million years. That's longer than dinosaurs have been extinct. That's longer than complex life has existed on land. And that's just our galaxy. Now look outward. Andromeda, our nearest large galactic neighbor, sits 2.5 million light-years away. That's not 2.5 million miles or kilometers. That's 2.5 million years at the speed of light. It's 25 times the width of the Milky Way. The distance is so vast that the light you see from Andromeda tonight left that galaxy before humans existed, before Homo sapiens, before Homo erectus, before any member of our genus walked the Earth. When the light now reaching your eyes began its journey, our ancestors were small-brained apes in Africa, just beginning to use primitive stone tools. To reach Andromeda with our fastest current spacecraft, the Parker Solar Probe, would require not millions, but billions of years, 3.7 billion years, to be exact. That's almost as long as life has existed on Earth. It's older than the oldest rocks on our planet's surface. It's a time span so long that the Sun itself will have exhausted its hydrogen fuel and begun swelling into a red giant before that journey would be even close to complete. And Andromeda isn't even far by cosmic standards. It's part of what astronomers call the local group, a gravitationally bound collection of more than 50 galaxies spanning about 10 million light-years. The local group is our cosmic neighborhood, the cluster of galaxies held together by mutual gravitational attraction. Besides the Milky Way and Andromeda, there's the Triangulum Galaxy, about 3 million light-years away, the third largest in the local group, with perhaps 40 billion stars. Then there are dozens of smaller dwarf galaxies, little galaxies with names like the Large Magellanic Cloud, the Small Magellanic Cloud, the Sagittarius Dwarf, the Sculptor Dwarf, each containing millions to billions of stars. These galaxies orbit around the Milky Way and Andromeda like moons around planets. They're small, dim, often irregular in shape, but they're galaxies nonetheless. each one an island of stars in the cosmic sea. Beyond the local group, the distances become so large that human language starts to fail. The next significant structure is the Virgo cluster, a massive collection of over 1,000 galaxies located about 55 million light-years away. 55 million light-years. At light speed, a journey that would span 55 million years. The Virgo cluster contains giant elliptical galaxies, some of the largest galaxies in the nearby universe, with trillions of stars each. And the Virgo cluster itself is just one part of the Virgo supercluster, which includes our local group as a tiny outlying member. The Virgo supercluster spans 110 million light-years, and that's not even among the largest structures in the universe. There are superclusters like the Laniakea supercluster, which spans 520 million light-years and contains about 100,000 galaxies. There are cosmic filaments, vast threads of galaxies stretching across billions of light-years. The observable universe itself extends about 93 billion light-years across, containing perhaps 2 trillion galaxies. These aren't numbers you can visualize. They're not distances you can comprehend by scaling up familiar things. Let me try anyway. If you shrank the Earth to the size of a grain of sand, roughly 1 millimeter across, the Sun would be about the size of a small marble, roughly 1 centimeter in diameter, sitting 22 meters away. The nearest star, Proxima Centauri, would be 6,000 kilometers distant. That's the distance from Los Angeles to London. On that scale, the Milky Way galaxy would be roughly the size of North America. And Andromeda? Andromeda would be 63 million kilometers away. That's about 40% of the distance from the Earth to the Sun at full scale. These ratios break the human ability to conceptualize. The human brain didn't evolve to process these scales. Our brains evolved to understand the distances between waterholes, between predators and prey, between one tree and another. The farthest our ancestors needed to think was perhaps a few days' walk, maybe 100 kilometers at most. Evolution gave us brains capable of abstract thought, capable of mathematics and physics, but it didn't give us intuitions that work at cosmic scales. So we're left with numbers that we can write down, that we can calculate with, but that remain fundamentally alien to our experience. But physics doesn't care about our intuitions. It only cares about what the math allows. And the math is brutally clear. The first and most fundamental barrier is the speed of light. Nothing with mass can reach it, let alone exceed it. This isn't an engineering problem or a matter of insufficient technology. It's a law woven into the fabric of reality itself, into the very structure of space-time. Einstein's special relativity, published in 1905, tells us that as an object with mass accelerates closer and closer to the speed of light, its relativistic mass increases. This isn't mass being added from somewhere else. It's a consequence of how energy and momentum work at high velocities. As velocity increases, the energy you're pumping into the object doesn't just make it go faster. More and more of that energy goes into increasing the object's relativistic mass instead of its velocity. The faster you go, the more energy you need to go even faster, and the relationship is nonlinear. It's exponential. The energy required to continue accelerating grows exponentially, approaching infinity as the velocity approaches light speed. Let's make this concrete. At 10% the speed of light, the increase in relativistic mass is only about 0.5%, noticeable but not prohibitive. At 50% the speed of light, relativistic mass increases by about 15%, significant but still manageable in principle. At 90% the speed of light, relativistic mass more than doubles. At 99%, it increases by a factor of about 7. At 99.9%, it's over 22 times the rest mass. At 99.99%, it's 70 times. At 99.999%, it's over 223 times. And this progression continues asymptotically. To actually reach the speed of light would require infinite energy, and the universe doesn't have infinite energy to give. The total mass energy of the observable universe is finite, enormous, beyond comprehension, but finite, and it wouldn't be enough. You can't brute force your way past this barrier no matter how advanced your engines become. You could have a propulsion system powered by harnessing the entire energy output of a star, and you still couldn't push a spaceship with mass to light speed. You could harness the energy of 1 billion stars, of every star in the galaxy, and the universe would still say no. The speed of light is not a speed limit like a speed limit on a highway, something you could break if you just had a fast enough car. It's a fundamental property of spacetime itself. Light travels at that speed because that's the speed at which causality propagates through the universe. It's the speed of cause and effect. Nothing with mass can reach it because reaching it would require infinite energy, and the universe doesn't do infinity in its accounting. But let's say, for the sake of argument, that we could get close. Really, really close. Let's imagine a spacecraft accelerating to 99.999% the speed of light. This isn't physically impossible, just practically impossible given energy constraints we'll discuss. At that velocity, relativistic effects become extreme. Time dilation, one of the strangest predictions of special relativity, kicks in with full force. For the travelers aboard that ship, time slows down dramatically relative to the outside universe. This isn't an illusion or a trick, it's real. Time genuinely passes more slowly for objects moving at relativistic speeds. This has been measured, tested, confirmed in countless experiments. Atomic clocks flown on airplanes run slightly slower than clocks on the ground. Particles called muons, created in the upper atmosphere by cosmic rays, should decay long before reaching the ground based on their half-life, but they don't because they're moving at relativistic speeds, and time dilation extends their lifespan from their own reference frame. At 99.999%, the speed of light, the time dilation factor, called gamma, is about 223. That means, for every year that passes on the ship, 223 years pass in the outside universe. So in principle, if you could build such a ship and survive the journey, you personally could reach Andromeda within a human lifetime, your lifetime. The journey would take about 2.5 million years from the perspective of someone watching from Earth, but for you on the ship, it would take only about 11,000 years. Still a long time, far longer than recorded human history, but at least it's within the realm of human comprehension. You could put people in some form of suspended animation, cryogenic, sleep perhaps, and they could wake up at their destination within their own lifetime, subjectively speaking. But here's the problem, the brutal, unavoidable problem that ruins even this optimistic scenario. While you age only thousands of years, the universe outside ages millions of years. Everyone you knew is dead. Everyone they knew is dead. Everyone they knew is dead. The civilization that built your ship, that designed it, that funded it, that waved goodbye as you left, has risen and fallen 100 times over. Languages have evolved beyond recognition. Entire species have evolved. The continents have drifted. The Earth itself may be unrecognizable. The sun is slightly hotter and brighter than when you left, enough to potentially make Earth uninhabitable in the far future, though probably not over a mere few million years. But human civilization, if it still exists, is utterly alien to you. You arrive at Andromeda a time traveler, not an explorer. You've escaped the distance, but not the time, and there's no going back, not to the world you left. The return journey would consume another few million years of external time. By the time you got home, if there even was a home, if Earth hadn't been consumed by the sun's expansion, or destroyed by asteroid impact, or rendered lifeless by some other catastrophe, you'd be returning to a planet and a species that had evolved beyond anything you could recognize. You'd be a fossil, a creature from the deep past visiting a future that has no place for you. This is the paradox of relativistic time dilation. It solves the travel time problem for the traveler, but it doesn't solve the mission problem. If the goal of spaceflight is to explore and return with knowledge, to maintain contact with home, to build a network of settlements connected by travel and communication, time dilation destroys that goal. Every journey becomes a one-way trip into the future. And there's another problem with time dilation that people often overlook. It doesn't help with the turnaround. Imagine you're traveling to Andromeda at 99.999% the speed of light. From your perspective, the journey takes about 11,000 years, but when you arrive, you're still moving at 99.999% the speed of light. If you want to stop, to actually arrive at Andromeda, rather than just shoot past it, you need to decelerate, and deceleration requires just as much energy as acceleration. You need to fire your engines in the opposite direction with the same total energy expenditure to bring yourself to rest relative to Andromeda. That means you need twice the fuel or twice the energy source, or you need to carry a second complete propulsion system. Either way, the already impossible energy requirements just doubled, and that's assuming you could reach those speeds in the first place, which you almost certainly cannot. The energy requirements are staggering beyond comprehension. Let's talk real numbers, the kind of numbers that make engineers weep and physicists shake their heads. The kinetic energy of an object in classical mechanics is 1/2 its mass times its velocity squared. That's the equation you learn in high school physics. But at relativistic speeds, you have to use the full relativistic equation. The total energy of a moving object is its rest mass energy, which is mass times the speed of light squared times the gamma factor. At low speeds, this reduces to the classical equation, but at high speeds, the gamma factor dominates, and the energy requirement skyrockets. Let's calculate. To accelerate a single kilogram of matter, just 1 kilogram, roughly the mass of a laptop computer, to 99.99%, the speed of light requires roughly 900,000 terajoules of energy. A terajoule is a trillion joules. To put that in perspective, the atomic bomb dropped on Hiroshima released about 63 terajoules. So, we're talking about the equivalent of more than 14,000 Hiroshima bombs worth of energy just to accelerate 1 kilogram to 99.99% of light speed. But we said 99.999%, didn't we? Let's recalculate for that. At 99.999%, you need about 2 million terajoules per kilogram. That's about 32,000 Hiroshima bombs per kilogram. Just to accelerate a laptop to that speed would require the energy equivalent of the entire world's nuclear arsenal several times over. Now let's talk about a realistic spacecraft. A small spacecraft with a crew, life support systems, scientific instruments, communications equipment, computers, hull, structure, everything you'd need for interstellar travel might have a dry mass, meaning without fuel, of 10,000 kilograms. That's 10 metric tons, which is actually incredibly optimistic. The Apollo lunar module, which supported 2 astronauts for a couple of days on the moon, had a mass of about 15 tons. A spacecraft capable of supporting a crew for thousands of years, even in suspended animation, would almost certainly be much heavier. But let's be generous and say 10 tons. To accelerate that 10-ton spacecraft to 99.999%, the speed of light requires about 20 petajoules. A petajoule is a quadrillion joules. That's roughly equivalent to the energy in 5 million barrels of oil. It's about the total energy consumption of a large city for a year. And remember, you have to decelerate too, so double it. 40 petajoules total. That's approximately the total energy consumption of the entire United States for about 3 months, just to move one small spacecraft to Andromeda and back. And that's not even counting the mass of the fuel itself, which brings us to the fuel problem, the rocket equation, the tyranny of exponentials that has plagued rocket designers since the dawn of spaceflight. Rockets work on a simple principle. You expel mass in one direction at high velocity, and Newton's third law pushes you in the opposite direction. The faster you expel the mass, and the more mass you expel, the greater your acceleration. But here's the problem. That expelled mass, the propellant, has to be carried with you at the start of the journey. And propellant has mass, which means you need energy to accelerate the propellant, along with the rest of the spacecraft, which means you need even more propellant to accelerate that propellant, which adds more mass, requiring more propellant still. This vicious cycle is described by the Tsiolkovsky rocket equation named after the Russian rocket pioneer who derived it in the late 19th century. The equation relates the change in velocity, called delta V, to the exhaust velocity of your engine, and the ratio of your starting mass to your ending mass. For low speeds, this isn't too bad. To reach orbit from Earth requires about 9 kilometers per second of delta V. Using chemical rockets with exhaust velocities around 4 kilometers per second, you need your rocket to be about 90% fuel by mass. That's why the Saturn V moon rocket was a gigantic tower of fuel with a tiny capsule on top. But for interstellar travel at relativistic speeds, the rocket equation becomes absolutely murderous. The exhaust velocity of a chemical rocket is limited by the energy content of chemical bonds, which is tiny compared to what we need. Even nuclear fusion, which releases energy by fusing light atomic nuclei into heavier ones, offers exhaust velocities of only a few percent of light speed at best. To reach 99% of light speed using fusion propulsion, even under the most optimistic assumptions, would require your spacecraft to be more than 99.99% fuel by mass. For every kilogram of payload, you'd need tens of thousands of kilograms of fuel. And we're not talking about reaching 99.999%. We're talking about barely reaching a few percent of light speed before the equation makes the fuel requirements absurdly impractical. You need something far more energetic, and the most energetic process available in physics is matter-antimatter annihilation. Antimatter is matter's mirror image. For every particle, there's a corresponding antiparticle with the same mass, but opposite charge and other quantum properties. When a particle meets its antiparticle, they annihilate completely, converting 100% of their combined mass into energy, according to Einstein's famous equation, E equals mc squared. This is the most efficient energy release possible in physics. Chemical reactions convert about 1/1000th of mass into energy. Nuclear fission converts about 0.1%. Nuclear fusion converts about 1%. Matter-antimatter annihilation converts 100%. You can't do better than that without changing the laws of physics. So antimatter seems like the ultimate fuel. But even antimatter doesn't save you from the rocket equation. To accelerate our 10-ton spacecraft to 99% of light speed using a perfect antimatter rocket, where all the annihilation energy goes into thrust with 100% efficiency, which is physically impossible, but let's assume it anyway, you would need about the same mass in antimatter and matter fuel combined as the final velocity you're trying to reach requires. The math works out to needing roughly equal masses of spacecraft and fuel for each increment of velocity. But we're trying to reach relativistic speeds, so the relativistic rocket equation applies, and things get worse. To reach 99.9% of light speed and then decelerate again, accounting for the changing mass of your spacecraft as you burn fuel, you would need several times the dry mass of your ship in antimatter-matter fuel. Let's say 50 tons of antimatter and 50 tons of matter for our 10-ton ship. That's 100 tons of fuel. Now here's the killer. Antimatter doesn't exist in nature in any significant quantity. There are tiny amounts produced in cosmic ray collisions in the upper atmosphere, but we're talking about a few atoms. There's possibly some trapped in the Earth's magnetic field, but again, negligible amounts. Every single atom of antimatter you would need for your fuel would have to be manufactured, and manufacturing antimatter is phenomenally expensive in energy terms. You create antimatter by smashing particles together at high energies and occasionally producing particle-antiparticle pairs. The most efficient antimatter production happens at particle accelerators like the Large Hadron Collider, and even there, the efficiency is abysmal. For every unit of energy you get back when the antimatter annihilates, you had to put in billions or trillions of units of energy to create it in the first place. The energy cost of producing the antimatter fuel vastly exceeds the energy the antimatter would provide. You'd need to harness the entire energy output of the sun for years, possibly centuries, just to produce enough antimatter for one ship. It's a thermodynamic dead end, a fuel that costs more to make than it gives you back. Some have proposed alternatives. Nuclear pulse propulsion, first seriously studied in a classified project called Project Orion in the 1950s and 60s involves detonating nuclear bombs behind your spacecraft and riding the shockwave. You're essentially surfing a series of nuclear explosions. It sounds insane, but the physics actually works. The bombs push against a massive metal pusher plate attached to the spacecraft by shock absorbers, and the accumulated impulse from thousands or millions of bombs could theoretically accelerate a very large spacecraft to a few percent of light speed. The advantage is you're not limited by the rocket equation in the same way, because each bomb provides a discrete push and doesn't have to be carried as propellant mass in the traditional sense. But there are problems. The engineering challenges are immense. The pusher plate would need to withstand millions of nuclear detonations, each one vaporizing a thin layer of its surface. The radiation shielding would need to protect the crew from both the bombs and the secondary radiation. And even in the most optimistic scenarios, nuclear pulse propulsion tops out at maybe 10% of light speed after using up thousands of nuclear weapons. At 10% of light speed, the journey to Andromeda takes 25 million years. Better than conventional rockets, but still nowhere near fast enough. Solar sails and laser-pushed light sails offer another approach. Instead of carrying fuel, you use photons, either from the sun or from powerful lasers built by the civilization you're leaving behind, to push an ultra-thin reflective sail. Photons carry momentum even though they have no mass, and when they reflect off a mirror, they transfer twice their momentum to it. A large enough sail with a small enough payload could in principle be accelerated to significant fractions of light speed by a powerful enough laser array. This concept has the huge advantage that you don't carry fuel at all. Your fuel stays behind, shooting photons at you. But there are severe problems. First, the sail has to be incredibly thin and light, which makes it fragile. Second, as you accelerate away from the laser, the beam diverges and weakens. Even a perfect laser beam spreads out due to diffraction, and over interstellar distances, the beam becomes vanishingly weak. You would need an absolutely enormous laser array, or an array of lasers covering a significant fraction of the inner solar system, to push a light sail to even 10 or 20% of light speed. Third, and this is the killer, you have no way to decelerate at the destination, unless you've somehow arranged for Andromeda to build a laser array to slow you down, which requires getting to Andromeda first to build it. You could carry a secondary sail and use the radiation from the destination star to slow down, but the deceleration would be gradual and weak. More likely, you're going on a one-way trip at high speed with no way to stop. You could use the sail to slow down by angling it to catch light from the destination star, but the deceleration would take an immensely long time because stars emit far less directional radiation than a focused laser. And you certainly can't come home. The laser that accelerated you is millions of light years behind you now, and getting farther every second. There's no way to turn around. These concepts, nuclear pulse propulsion, laser sails, might work for sending tiny probes at a fraction of light speed to nearby stars within our own galaxy. In fact, there's a project called Breakthrough Starshot that aims to do exactly that, sending tiny gram-scale probes with sails pushed by ground-based lasers to Alpha Centauri, 4 light-years away, at 20% of light speed, arriving in about 20 years. It's ambitious and faces enormous technical challenges, but it's not fundamentally impossible. But when you scale these concepts to intergalactic distances, they collapse completely. The laser beam divergence becomes overwhelming. The travel times, even at high fractions of light speed, become millions of years. The engineering margins become impossibly thin. Every propulsion system we can imagine, even in pure theory, fails when confronted with the gulf between galaxies. But let's say you solve the energy problem. Let's say you invent a propulsion system that runs on something we haven't discovered yet, some new physics we don't know about, something that doesn't violate known laws, but somehow provides the absurd amounts of energy required in a compact, controllable form. Let's say you have a magic engine. You still face another insurmountable barrier, and it's one that most people don't think about. The universe will kill you. At relativistic speeds, Space is not empty. It's filled with gas, dust, cosmic rays, stray atoms of hydrogen and helium, tiny grains of silicate and carbon. Under normal circumstances, these particles are harmless. The interstellar medium, the space between stars, is one of the best vacuums in the universe, far better than anything we can create in a laboratory. The density is about 1 atom per cubic centimeter on average, though it varies. In some regions, dense molecular clouds, it's thousands of atoms per cubic centimeter. In other regions, hot bubbles blown by supernovae, it's 1 atom per 100 or 1,000 cubic centimeters. But even at its most diffuse, space is not completely empty. There are particles, and velocity changes everything. Imagine you're traveling at 99.99% the speed of light. From your perspective, due to the relativistic effects we talked about, you're at rest, and it's the universe moving past you at 99.99% of light speed. Every atom of hydrogen in your path is coming at you at that same enormous velocity. The relative kinetic energy of even a single hydrogen atom becomes enormous. A hydrogen atom has a mass of about 1.7 times 10 to the minus 27 kilograms. At 99.99%, the speed of light, the relativistic kinetic energy of that atom is roughly 10,000 times its rest mass energy. That single atom hits your ship with the kinetic energy of a high-velocity rifle bullet. A grain of dust, something weighing a milligram, a millionth of a kilogram, impacts with an energy of about 50,000 terajoules. That's roughly the energy of 1,000 Hiroshima bombs. A grain of dust, a mote you can barely see, a pebble the size of your fingernail, weighing maybe a gram, would strike with the force of millions of nuclear weapons. It would vaporize anything it touched, and probably the entire spacecraft along with it. And space, while mostly empty, is not completely empty. You will hit things. The interstellar medium contains roughly 1 atom per cubic centimeter. That doesn't sound like much, but consider the cross-sectional area of your spacecraft. Let's say it has a frontal area of 10 square meters, which is quite small for a crewed vessel. That's 100,000 square centimeters. As you travel through space, you're sweeping out a volume of 100,000 cubic centimeters per centimeter of forward travel. At 1 atom per cubic centimeter, that's 100,000 atoms per centimeter. At 99.99% of light speed, you're traveling roughly 30 billion centimeters per second. So you're hitting about 3 trillion atoms per second. Each one is a bullet. 3 trillion bullets per second, constantly, without pause, slamming into your hull. The cumulative damage would be catastrophic within seconds. But it's actually worse than that, because we haven't even talked about cosmic rays. Cosmic rays are high-energy particles, mostly protons, accelerated to enormous speeds by violent events like supernova, pulsars, active galactic nuclei. They're rare compared to the ambient hydrogen of the interstellar medium, but they're far more energetic. Some cosmic rays have been detected with energies exceeding 10 to the 20th electron volts, which is roughly the kinetic energy of a baseball thrown at 60 miles per hour, concentrated in a single subatomic particle. These are called ultra-high energy cosmic rays, and we don't fully understand where they come from or how nature accelerates them to such absurd energy. When one of these particles hits the Earth's atmosphere, it creates a shower of thousands of secondary particles. Now imagine you're traveling at 99.99% of light speed. From your perspective, you're at rest, and the cosmic rays are coming at you even faster than they normally are, blue shifted to even higher energies by relativistic effects. The flux of cosmic rays increases. Their energy, as measured in your reference frame, becomes catastrophic. A single ultra-high energy cosmic ray hit could potentially damage or destroy critical systems, and there's no predicting them, no avoiding them. Shielding becomes impossible. You can't build armor thick enough to protect against relativistic impacts without making your ship so massive that it becomes impossible to accelerate in the first place. Remember, every kilogram of shielding is a kilogram you have to accelerate, which requires more fuel, which adds more mass, which requires more fuel. The rocket equation kills you before you even launch. You can't use magnetic fields to deflect charged particles, which most of this stuff is, because the energies involved are too high. The magnetic field strength required to deflect a relativistic hydrogen atom approaching at near light speed would need to be stronger than anything we can generate, and maintaining such a field would itself require enormous energy. And magnetic fields don't stop neutral particles like neutrons or photons anyway. You can't dodge because you can't detect obstacles fast enough at near light speed. The light from an object ahead of you, the light that would warn you of its presence, only reaches you moments before you collide with it, far too late to react. Your senses are effectively blind to anything directly ahead. By the time you see it, you've already hit it. Some have proposed using a small, expendable shield ahead of the main spacecraft, something that would take the hits and vaporize, protecting the ship behind it. But that shield itself becomes part of the mass you have to accelerate, and it would need to be replenished constantly as it erodes. And any impact energetic enough to vaporize the shield creates a cloud of plasma expanding at relativistic speeds, which then hits your main spacecraft anyway. You can't win. Space itself becomes a sandblaster, moving at near light speed, and your ship is the target. The faster you go, the deadlier space becomes. At a few percent of light speed, this is a problem, but maybe manageable. At 99%, it's lethal. At 99.999%, it's instantly catastrophic. Then there's the problem of navigation. At these speeds, your view of the universe distorts in bizarre ways due to relativistic effects. Light from stars ahead of you blue shifts into high-energy gamma rays and X-rays because of the Doppler effect. From your perspective, you're moving toward those stars at near light speed, so their light is compressed in wavelength and increased in energy. What was visible, light becomes ultraviolet, then X-rays, then gamma rays. Meanwhile, light from behind redshifts into low-energy radio waves and becomes invisible. The stars themselves appear to cluster in front of you due to an effect called relativistic aberration, where the apparent position of objects shifts due to your motion. The entire sky seems to compress into a bright spot ahead of you, with everything behind you disappearing. You're navigating through a distorted, radiation-soaked version of the cosmos, where your normal instruments don't work. You can't use optical telescopes because all the light is blue-shifted out of the visible range. You need gamma-ray detectors to see where you're going, and gamma rays are notoriously hard to focus and image precisely. Your navigation becomes guesswork, and a single mistake in trajectory, an error of even a fraction of a degree, could send you off course by thousands of light-years over the span of an intergalactic journey. And you'd better hope your systems don't fail, because there's no rescue. No one can catch up to you. You're traveling at near light speed. Any rescue ship would have to accelerate to the same velocity, which requires the same impossible energy expenditure. And by the time anyone realized, you were in trouble. Assuming you could even send a distress signal back against your direction of motion, you'd be millions of light years away and millions of years in the future. No one can send help. You are alone in a way no human has ever been alone. Alone in the truest sense, causally disconnected from the rest of humanity by the combination of distance and time. And all of this, every single thing we've discussed so far, assumes the universe stays still. It doesn't. The universe is expanding, and this expansion isn't a detail or a minor complication. It's the death sentence for intergalactic travel. Edwin Hubble discovered in 1929 that galaxies are moving away from us, and the farther away they are, the faster they're receding. He measured this by looking at the light from distant galaxies and noticing that it was redshifted, stretched to longer wavelengths. This redshift is proportional to distance. Nearby galaxies show little redshift. Distant galaxies show enormous redshift. Hubble interpreted this correctly as evidence that the universe itself is expanding. Space is stretching, and galaxies are being carried along with it, like raisins in rising bread dough. This isn't because galaxies are flying through space away from us. It's because space itself, the fabric of the universe, the metric of space-time, is expanding. New space is being created between galaxies. This is hard to visualize because we don't have everyday experience with space itself expanding. We are used to things moving through space, not space itself growing. But that's what's happening, and the rate of this expansion is described by the Hubble constant, usually denoted h0. The current best measurements put the Hubble constant at about 70 kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light-years. So what this means is that for every megaparsec of distance, space is expanding such that objects separated by that distance are receding from each other at 70 kilometers per second. That doesn't sound like much. 70 kilometers per second is only about 0.023% the speed of light. But here's the key thing. It scales. For every megaparsec, you add another 70 kilometers per second. At 2 megaparsecs, objects recede at 140 kilometers per second. At 10 megaparsecs, 700 kilometers per second. At 100 megaparsecs, 7,000 kilometers per second, about 2.3% of light speed. At 1,000 megaparsecs, 70,000 kilometers per second, about 23% of light speed. And at about 4,200 megaparsecs, roughly 13.7 billion light-years, objects are receding at the speed of light itself. Beyond that distance, objects recede faster than light. Now you might think this violates special relativity, which says nothing can move faster than light, but it doesn't. Special relativity says nothing can move through space faster than light, but space itself can expand at any rate. There's no speed limit on the expansion of space. The galaxies aren't moving through space faster than light. The space between us and them is growing faster than light can cross it. It's a subtle but crucial distinction, and it has profound consequences. This creates something called the cosmic event horizon, also sometimes called the Hubble sphere, at its simplest definition, though the true event horizon is a bit more complex. Beyond a certain distance, currently calculated at about 16 to 17 billion light-years, depending on how you define it precisely, galaxies are receding from us faster than light. No signal we send, no spacecraft we launch, nothing can ever reach them. They are causally disconnected from us. We can see their light that was emitted billions of years ago when they were closer and the universe was younger and denser, but we can never interact with them. We can never send a message that will arrive. We can never travel there. They are beyond the edge of the reachable universe, permanently and forever. And that edge is not fixed, because the expansion isn't just continuing, it's accelerating. This was discovered in 1998 by 2 teams of astronomers studying distant supernovae. They expected to find that the expansion of the universe was slowing down over time due to the gravitational attraction of all the matter in the universe pulling back on the expansion. Instead, they found the opposite. The expansion is speeding up. Distant supernovae were farther away than they should be if the expansion rate had been constant or slowing. Something is pushing the universe apart, overcoming gravity, accelerating the expansion. We call this something dark energy, though we don't really know what it is. It's not a substance or a field in the traditional sense. It's more like a property of space itself, an energy density inherent in the vacuum. The cosmological constant, first proposed by Einstein, and then abandoned, then resurrected. Whatever it is, dark energy makes up about 68% of the total energy content of the universe, and it's causing the expansion to accelerate. This acceleration has a terrifying consequence. The cosmic event horizon is shrinking, not in absolute distance from us, but in terms of which galaxies are inside it. Galaxies that are currently within reach, in the sense that a light speed signal sent today could eventually reach them, will eventually cross the horizon and be lost forever. As the expansion accelerates, more and more of the universe becomes unreachable. Even if we launched a light-speed probe today toward a distant galaxy just inside the horizon, the expansion of space might carry that galaxy beyond the horizon before the probe could arrive. Space is being created between us and the target faster than the probe can cross it. The probe would be like a person running on a treadmill that's accelerating. You can run as fast as you want, but if the treadmill speeds up faster than your maximum speed, you'll never reach the front. You'll run forever and make no progress. That's what happens to a spacecraft. Even a light-speed spacecraft trying to reach a galaxy beyond the event horizon, it travels forever through expanding space and never arrives. Now here's the crucial point for our discussion. Our local group, the gravitationally bound cluster of galaxies that includes the Milky Way, Andromeda, Triangulum, and dozens of smaller dwarf galaxies, is held together by gravity. The mutual gravitational attraction between these galaxies is strong enough to overcome the expansion of space on these scales. Gravity is pulling them together faster than expansion is pushing them apart. So Andromeda is actually moving toward us, not away. It's approaching at about 110 kilometers per second. In about 4 billion years, give or take a billion, Andromeda and the Milky Way will collide. Not collide in the sense of stars smashing into each other, because stars are so far apart that even when galaxies merge, actual stellar collisions are rare. But the two galaxies will pass through each other, their mutual gravity disrupting each other's structure, stripping away stars, flinging some into intergalactic space, pulling others into new orbits. The supermassive black holes at the centers of both galaxies will eventually spiral together and merge, releasing gravitational waves so powerful that they'll ripple across the universe. Over the course of billions of years, the two galaxies will merge into a single giant elliptical galaxy. Astronomers have already nicknamed it Milkomeda, a portmanteau of Milky Way and Andromeda. It will be a beautiful, chaotic process, though unfortunately, Earth's sun will likely have already become a red giant by then, rendering Earth uninhabitable, so no humans will be around to witness it unless we've spread beyond our solar system. This is happening because gravity dominates over cosmic expansion at the scale of the local group. The local group is about 10 million light-years across. Within that volume, gravity wins. So, in principle, with a heroic and probably impossible effort, galaxies within the local group are reachable. Not easily, not with any technology we can currently imagine, not without solving all the problems we've discussed: energy, shielding, navigation, time dilation. But the universe doesn't actively prevent it. The space between us and Andromeda is not expanding faster than light. It's not expanding at all on net, because gravity is contracting it. If you could somehow launch a spacecraft toward Andromeda, and if that spacecraft could survive the journey, and if you didn't care about the millions of years of external time that would pass, you could in theory reach it. But beyond the local group, forget it. The next major galaxy cluster, the Virgo cluster, 55 million light-years away, is receding from us. Cosmic expansion is carrying it away. The space between us and Virgo is expanding. Not fast, only about 1,200 kilometers per second, about 0.4% the speed of light. But it's expanding nonetheless, and over the time it would take to travel there, even at relativistic speeds, Virgo will have moved farther away. By the time you're halfway there, having traveled for tens of millions of years, Virgo is now farther than it was when you started. You're chasing a target that's running away from you. It's still technically reachable, barely, because it's receding slower than light, but the margin is slim, and the farther out you look, the faster galaxies recede. The Coma cluster, 300 million light-years away, is receding at about 7,000 kilometers per second, over 2% of light speed. Galaxy clusters a billion light-years away are receding at 7% of light speed. At 2 billion light-years, 14%. At 4 billion light-years, 28%. By the time you get to distances of 10 or 13 billion light-years, galaxies are receding at substantial fractions of light speed, and beyond about 16 billion light-years, they're receding faster than light itself. Those galaxies are gone, permanently, unreachable. No matter what you do, no matter what technology you invent, you cannot reach them because the space between you and them is expanding faster than you can possibly cross it. So, the reachable universe, the part of the cosmos we could ever hope to visit, even in principle, is limited to the local group, 50-some galaxies, the Milky Way, Andromeda, Triangulum, and a collection of dwarf galaxies, most with fewer than 1 billion stars, some with only a few million. That's it. That's all we get. Out of the 2 trillion galaxies in the observable universe, we have permanent access to maybe 50. That's 0.000002, 5%. 99.9999975% of the galaxies in the universe are forever beyond our reach. They exist. We can see them. We can photograph them, study them, measure their properties, understand their evolution, but we can never go there. They might as well be in a different universe, because for all practical purposes, they are, and it gets worse. Because the expansion is accelerating, the local group is going to become more isolated over time. Right now, we can see about 2 trillion galaxies. In 100 billion years, most of those galaxies will have receded beyond the cosmic event horizon. Their light will be redshifted into nothingness, stretched to such long wavelengths that it becomes undetectable. The night sky will darken. Fewer and fewer galaxies will be visible. Eventually, in the far future, trillions of years from now, all the galaxies outside the local group will have disappeared from view, not because they've been destroyed, but because the light they emitted will have been redshifted beyond detection, and no new light from them will ever reach us. The universe will have carried them beyond our cosmic horizon. Future astronomers in Milkomeda, the merged galaxy born from the Milky Way, and Andromeda, will look up at the sky and see only their own galaxy. They'll see the stars of Milkomeda, billions or trillions of them, spread across the sky. But beyond that, nothing. Empty space, darkness. If a civilization arose for the first time in that era, a civilization that had never existed before, they would have no way to know that other galaxies exist or ever existed. They would look at the sky and see one galaxy, their galaxy, surrounded by darkness. They'd have no evidence for the Big Bang because the cosmic microwave background, the afterglow of the Big Bang, will have been redshifted into undetectability. They'd have no distant galaxies to measure, no Hubble expansion to observe. They would think the universe consists of one galaxy in an infinite static void. They would be wrong, but they'd have no way to discover their error. The universe would have hidden its own history from them. This is actually a profound and somewhat terrifying realization. We live in a special epoch, cosmologically speaking. We exist at a time when the universe is old enough that we can see the cosmic microwave background, young enough that distant galaxies are still visible, and structured enough that galaxies have formed and stars have created heavy elements necessary for planets and life. In the far future, much of the evidence for the Big Bang and the large-scale structure of the universe will have vanished. Future civilizations will be cosmologically impoverished, unable to deduce the true nature of their universe. We are lucky, in a sense, to exist now. We can see the universe in its full glory, even if we can't reach most of it. And this is the fate awaiting anyone who remains in the local group. Our descendants, if they survive the merger of the Milky Way and Andromeda, if they endure the death of the sun and the fading of the stars, if they find ways to harness energy from sources other than main sequence stars, perhaps from black holes or dark matter or some exotic physics we haven't discovered, will inherit a lonelier universe with every passing billion years. One by one, the galaxies beyond will wink out, their light stretched into oblivion. The cosmic horizon will shrink until nothing remains outside the gravitational bubble of the local group. And if our descendants want to travel, their entire reachable universe will be that 10 million light-year span. That's it. That's all they get. 50-something galaxies. Most of them tiny dwarfs, barely worthy of the name. Andromeda, Triangulum, the remnants of the Milky Way merged into Milkomeda, and a handful of smaller companions orbiting like moths around a flame. Beyond that, an infinite void, expanding, accelerating, empty. There is no escape. There is no secret door hidden in the equations. The universe has drawn the boundaries in spacetime itself, and they're permanent. Let's pause for a moment and consider what this really means. Imagine you're a member of an advanced civilization 1 trillion years from now. Your ancestors merged with artificial intelligence, uploaded their consciousness into computational substrates, found ways to survive the death of stars by harvesting energy from the quantum vacuum or the rotation of black holes. You're functionally immortal, at least as immortal as the universe allows. You have technology that would seem like magic to us. You can manipulate matter at the atomic level, create megastructures that span solar systems, maybe even star systems. You have perfect knowledge of physics as far as it can be known. You've pushed every law to its limit, and you look up at the sky and see nothing, your galaxy, and only your galaxy. You have records, ancient records from a time when other galaxies were visible, but they're just stories now, myths. You can't see those galaxies anymore. You certainly can't reach them. You're alone. Your entire civilization, all its knowledge, all its achievements, all its dreams, confined to one galaxy, and that galaxy itself is dying. The stars are going out one by one. The small red dwarfs will burn for trillions of years, but even they will eventually exhaust their fuel. Black holes will be the last sources of energy, evaporating through Hawking radiation over timescales of 10 to the 100 years and beyond. And you can't leave. You're trapped. The universe has become a prison, and the walls are absolute. This is hard to accept on a visceral, emotional level. Humans are explorers. We're wanderers. It's written into our DNA. Our ancestors left Africa 50,000 years ago and spread to every corner of the earth. We crossed oceans we couldn't see the other side of, in boats that could barely be called boats, with no knowledge of what lay beyond. We climbed mountains because they were there. We went to the moon not because it was easy, as Kennedy said, but because it was hard. Our entire history as a species is a story of pushing boundaries, of reaching beyond what seems possible. We've overcome plague, famine, ice ages, the vacuum of space. We've split the atom and decoded the genome. We've built machines that can think, and now we're being told that the ultimate boundary, the edge of the local group, is unbreakable. That 99.999999% of the galaxies in the universe are forever beyond our reach, no matter what we do, no matter how clever we are, no matter how advanced we become. It feels wrong. It feels like giving up. It feels like the universe is taunting us, showing us wonders, and then placing them behind unbreakable glass. But this isn't cruelty. The universe is not malicious. It's not designed to thwart us because it's not designed at all. It simply is, governed by laws that emerged from the initial conditions of the Big Bang and the fundamental constants of nature. The speed of light is finite, 300 million meters per second, because that's the structure of spacetime. Light travels at that speed because that's the speed at which causality propagates through the universe, the speed at which cause and effect can spread. It's not arbitrary. It's woven into the metric of spacetime itself. The universe expands because the energy density of the vacuum, dark energy, has a particular value that drives acceleration. Galaxies are separated by vast distances because the initial quantum fluctuations in the early universe, inflated by cosmic inflation in the first fraction of a second, seeded density variations that eventually collapsed into galaxies, and the distribution of those fluctuations determined where galaxies formed. None of this was arranged to thwart us. We simply live in a universe where intergalactic travel happens to be impossible for beings made of matter and bound by the same physical laws as everything else. And yet, there's something profound in that impossibility. We live in an age, this particular epoch in cosmic history, where we can see the universe. We have telescopes, Hubble, James Webb, radio telescopes, gravitational wave detectors that can capture light and signals from galaxies billions of light years away. We can measure the cosmic microwave background, photons that have been traveling for 13.8 billion years, nearly the entire age of the universe, carrying information about the Big Bang encoded in their temperature fluctuations. We can deduce the existence of dark matter from the rotation curves of galaxies and the gravitational lensing of light. We can infer the presence of dark energy from the accelerating expansion. We know about exoplanets orbiting other stars, thousands of them now, whole planetary systems. We've detected gravitational waves from colliding black holes and neutron stars, ripples in spacetime itself, confirming Einstein's century-old prediction. We understand the life cycle of stars, from their birth in collapsing molecular clouds to their deaths as white dwarfs, neutron stars, or black holes. We know the history of the universe from fractions of a second after the Big Bang to today. We have photographs of galaxies as they were billions of years ago, light that traveled across the cosmos to reach our eyes. We are, in a very real sense, looking back through time every time we look up at a dark sky, and we know with mathematical certainty that what we see is almost entirely unreachable. We are witnesses to a cosmic expanse we cannot touch. We can study it, measure it, understand it, but we cannot visit it. It's like being given a library containing every book ever written and being told you can read any of them, but you can never leave the library. And the library itself is slowly shrinking, the books on the outer shelves disappearing one by one, unreachable, gone. But you still have the books nearby. You still have knowledge. You still have understanding. This is the paradox of modern cosmology. We understand the universe better than any generation before us, better than Newton or Galileo could have dreamed, better than Einstein imagined, though he laid the foundations. And that understanding has revealed the limits of what we can ever do. We have seen the prison walls, and they are made of the structure of spacetime itself, enforced by the laws of relativity and thermodynamics and the expansion of the universe. There is no tunnel through them, no ladder over them, no secret passage. They are absolute. Wormholes require exotic matter we've never seen and energies we can't produce. Warp drives require manipulating spacetime on scales that may be fundamentally impossible. Faster than light travel violates causality and would allow time travel into the past, creating paradoxes the universe seems designed to prevent. Every loophole we can imagine in the equations either requires physics we don't have access to or collapses under closer scrutiny. And perhaps that's okay. Perhaps it has to be okay because we don't have a choice. The universe is what it is. The laws of physics are what they are. We didn't write them. We can't rewrite them. We can only discover them and work within their boundaries. And within those boundaries, there's still so much we can do. We can explore our own solar system. We can send probes to the outer planets, to the Kuiper belt, to the Oort cloud. We can study asteroids and comets, the primordial building blocks of planets. We can search for life on Mars, on the moons of Jupiter and Saturn, on Enceladus and Europa and Titan. We can build telescopes that peer deeper into space and farther back in time. We can study the cosmic microwave background with ever greater precision, extracting information about the first moments of the universe. We can detect more gravitational waves, opening a new window onto violent cosmic events. We can discover more exoplanets and characterize their atmospheres, searching for biosignatures, signs of life beyond Earth. And if we survive long enough, if we don't destroy ourselves through war or environmental collapse or some other catastrophe of our own making, we can spread within our own galaxy. The Milky Way contains 200 to 400 billion stars. Most of them probably have planets. If even a tiny fraction of those planets are habitable, that's millions or billions of worlds. We could, in principle, send generation ships to nearby stars, not traveling at relativistic speeds, but at a few percent of light speed, which is difficult but maybe not impossible with technologies like nuclear pulse propulsion or fusion drives. The journey would take centuries or millennia, but generation ships could potentially make it. We could seed the galaxy with human descendants or post-human descendant, or artificial intelligences carrying human knowledge and culture. Over millions of years, we could spread throughout the Milky Way, and then, over billions of years, throughout the local group. Andromeda has 1 trillion stars. Triangulum has 40 billion. The dwarf galaxies have millions to billion. That's more than enough. That's more worlds than we could ever explore, even with millions of years and millions of ships. So maybe the real question isn't why we can't reach the distant galaxies. Maybe the real question is why we feel we need to. Is it greed, ambition, curiosity, all of the above? We live in a galaxy with hundreds of billions of stars, in a local group with trillions of stars, and that's not enough? We need the Virgo cluster too. We need the Coma cluster, the Fornax cluster, the galaxies billions of light years away. Why? What would we do there that we can't do here? The honest answer is nothing. There's nothing in Virgo or Coma that isn't also in the Milky Way or Andromeda. Stars are stars, planets are planets, black holes are black holes. The physics is the same everywhere. The chemistry is the same. The laws don't change from one galaxy to another. If we're looking for resources, our galaxy has more than we could use in a billion lifetimes. If we're looking for knowledge, we can learn everything we need to know by studying our own cosmic neighborhood and observing the rest. If we're looking for life, for other civilizations, we should start by searching our own galaxy. And if we find nothing here, the odds of finding something in another galaxy are vanishingly small anyway. The distances between civilizations, if they exist, are probably far greater than the distances between stars, perhaps greater than the distances between galaxies. So maybe the desire to reach other galaxies isn't about practicality, it's about something deeper. It's about the human, or perhaps more broadly, the sentient need to know that there are no boundaries, that nothing is off limits, that the universe is open, infinite, explorable. To be told that something is unreachable, even in principle, feels like a violation of that need. It feels like the universe is saying no, and we're not used to hearing no from the universe. We're used to problems having solutions. We're used to barriers being temporary, waiting to be overcome by the next generation or the generation after that. But this barrier isn't temporary. It's permanent, and that permanence is hard to swallow. There's also an element of existential dread in the realization if we're confined to the local group, and if the local group will eventually become an isolated island in an expanding void, then in a very real sense, we're watching the universe die around us. Not die in the sense of ending, but die in the sense of becoming unreachable, invisible, gone from our perspective. The cosmos is committing a slow suicide by expansion, tearing itself apart, and we're powerless to stop it or escape it. Every billion years, the universe becomes a little lonelier, a little emptier, a little darker, and eventually, trillions of years from now, even the stars in our own galaxy will die. The universe will enter an era called the degenerate era, where the only objects are white dwarfs, neutron stars, and black holes, slowly radiating away their energy. Then, the black hole era, where even black holes evaporate through Hawking radiation. And finally, the dark era, where the universe is nothing but photons and neutrinos, and perhaps some exotic particles spread so thin that they effectively never interact. An infinite, cold, dark void, and we can't leave. We're stuck here for the ride, watching the universe wind down like a clock running out of spring. But here's a thought. Maybe that's the point. Maybe the fact that the universe is temporary, that stars die, that galaxies recede, that everything has an ending, is what gives it meaning. If the universe were infinite and eternal and fully explorable, would it matter as much? Would we care as much about understanding it? There's a beauty in transience, in impermanence. The Japanese have a concept called mono no aware, the pathos of things, a sensitivity to the ephemeral nature of beauty. Cherry blossoms are beautiful precisely because they last only a week or two before falling. If they bloomed year-round, would we cherish them as much? Maybe the universe is the same. Maybe the fact that we exist in this brief cosmic moment where galaxies are visible and stars are burning and life is possible makes it all the more precious. We're here, now, in this narrow window of time and space, and we can see wonders that no future civilization will ever see. We can study a universe full of galaxies, full of structure, full of light. That's a gift, even if it comes with the knowledge that most of it is beyond our reach. And there's another perspective. We're not just observers of the universe. We're part of it. We're made of atoms forged in the cores of ancient stars, scattered by supernovae, reformed into planets, and eventually into living beings. We are literally stardust. As Carl Sagan famously said, the universe has, through us, become conscious of itself. Atoms have arranged themselves into patterns complex enough to contemplate their own origin. That's extraordinary. That's maybe the most extraordinary thing in the universe. And the fact that we can understand our cosmic prison, that we can map its walls and measure its dimensions and comprehend why they exist, is itself a kind of freedom. We may not be able to leave, but we can know, we can understand, and maybe that's enough. Consider what we've accomplished already. A species that evolved on the savannas of Africa, that spent most of its history struggling to survive. to find food and water and shelter, has in the span of a few centuries figured out the structure of spacetime, the age of the universe, the nature of stars and galaxies. We've sent robots to other planets. We've looked into the hearts of atoms and found quarks and gluons. We've detected particles predicted by theory decades before we could build machines sensitive enough to find them. We've simulated the evolution of the universe on computers, watched galaxies form and stars ignite in virtual space. We've created artificial intelligence that can recognize patterns we can't, solve problems we can't, beat us at games we invented. And we're not done. We're still learning, still discovering, still pushing. That's the real human story. Not that we can travel to other galaxies, but that we want to, and that even though we can't, we don't stop asking questions. So maybe the impossibility of intergalactic travel isn't a tragedy. Maybe it's a challenge of a different kind. Not a challenge to overcome through engineering, but a challenge to accept through understanding. Can we be satisfied with knowledge without possession? Can we appreciate beauty without touching it? Can we be content with our cosmic neighborhood, vast as it is, without needing to conquer the entire universe? These are philosophical questions, not scientific ones, but they're worth asking. And there's one more thing to consider. We don't know everything. Our understanding of physics is incomplete. We know general relativity describes gravity beautifully on large scales, but breaks down at quantum scales. We know quantum mechanics describes the subatomic world precisely, but doesn't incorporate gravity. We don't have a theory of quantum gravity, a unified framework that works at all scales. String theory, loop quantum gravity, these are attempts, but they're not proven. We don't fully understand dark matter. We've detected its gravitational effects, but we don't know what it's made of. We don't understand dark energy at all. We know it's causing the expansion to accelerate, but we don't know why or what it is. These gaps in our knowledge might hide surprises. Maybe, just maybe, there's something we're missing, some aspect of physics we haven't discovered yet. That would change the picture. Not in a magical, wishful thinking way, but in a genuine, unexpected discovery that opens new possibilities. History has shown us that this happens. Newtonian mechanics seemed complete until Maxwell's equations revealed the finite speed of light. Classical physics seemed comprehensive until quantum mechanics revealed the probabilistic nature of reality. General relativity seemed to rule out an expanding universe until Hubble observed it. The universe has surprised us before. Maybe it will again, but we can't bank on that. We can't assume the universe will hand us a loophole just because we want one. We have to work with the physics we know, and the physics we know says intergalactic travel beyond the local group is impossible. The speed of light is a hard limit. The expansion of the universe is real and accelerating. The energy requirements for relativistic travel are prohibitive. The hazards of interstellar space are lethal. The time dilation effects are insurmountable for maintaining civilizational continuity. Every way we've looked at the problem, the answer comes out the same. We're not going to Virgo. We're not going to Coma. We're not going to the billions of galaxies beyond. They're beautiful. They're fascinating. They're worth studying, but they're not reachable. They're part of the observable universe, but not part of the accessible universe. And that's a distinction we have to learn to live with. There's a certain melancholy in that knowledge, a weight to it. To know that something exists, to see it in photographs taken by telescopes orbiting Earth or sitting on mountaintops, to measure its distance and composition and age, to understand its structure and evolution, and yet to know with absolute mathematical certainty that you will never reach it, that no human will ever reach it, that no descendant of humanity, no matter how advanced, will ever reach it, that it exists in a space that might as well be a different universe because the expansion of space-time has placed it permanently out of reach. Every spiral galaxy beyond the local group, every grand design spiral with its sweeping arms of stars and dust, every elliptical giant with its trillions of ancient suns, every irregular dwarf, every cluster and supercluster, all those structures spanning billions of light years, the cosmic web itself, filaments of galaxies stretching across the universe like neurons in a vast brain. They exist, they're real, they're out there, and they're forever separated from us by the expanding void. We are the first generation of humans to fully grasp the scale of the universe and the permanence of our isolation within it. Ancient humans looked up and saw the stars as points of light on a celestial sphere, close enough to touch if you could just climb high enough. Medieval astronomers thought the stars were perhaps millions of miles away, vast distances, but not inconceivable. Early modern astronomers realized the stars were light years away, distances that light itself takes years to cross, and we, in the 20th and 21st centuries, have mapped the universe to its edges and realized that most of it is not just far away, but unreachable in principle, locked behind a horizon made of expanding space-time. We know too much. We've done the math, we've measured the distances, the expansion rate, the energy requirements, we've run the simulations and checked the calculations 1,000 times, and every time the answer is the same. The cosmos is vast, but our corner of it is small and bounded. We are islanders on a tiny archipelago in an infinite ocean that's getting wider, and the currents are pulling every other island away from us faster than we can ever swim. In time, even the sight of those islands will vanish, redshifted into darkness, and we'll be alone with only our own islands, our own local group, our 50 galaxies and an infinite, empty sea. We stand at the edge of the reachable universe, staring into a void we will never cross, holding instruments that can see 13.8 billion years into the past but cannot change the future written in the equations of relativity and cosmology. The universe is vast beyond comprehension, filled with wonders we have only begun to glimpse, islands of light separated by oceans of darkness, and we will spend eternity here, in our little gravitational corner, witnesses to a cosmos we cannot explore. The galaxies will still shine in our telescopes, their light reaching us across billions of years. They'll still be beautiful, but they'll remain forever what they are now: images, data, light from places we will never go.